Alright, looks like we're live. Okay, let's continue. Let me open the table of content first. Okay, we are still on chapter 17 on homework simulation here. Let me check that. Okay, we are in this section and we have to take a look at this. We need to take a look at this too. We need to take a look at this, the first video, and then trying out the ordering. Now let's try coalescing of release. Okay, increasing the number of random allocation to 1000. Okay, looks like we have multiple questions here. What happened to larger allocation request over time? I'm assuming we use the, what is it called? This default flag value, like the header size or the, what is it called? The policy for searching the free list, and then the set 0. But with this random allocation of 1000. Okay. I think let's just analyze this rather than putting that, rather than trying to predict manually, because yeah, 1000 is quite a lot. What happened to larger allocation request? Allocation request. Okay. Over time. Okay, and then what the difference when using coalescing and non-coalescing for the free list? Okay, something like that. What difference in outcome do you see? Okay. How big is the free list over time in each case? How big the free list over time when using coalescing and non-coalescing for the free list? Does the ordering of the list matter in this case? The ordering matter in this case? I mean, if we are using base, even when we are using base, when we are coalescing the free list, there might be some difference, Does the ordering of the list matter? Okay. The ordering of the list matter when coalescing or non-coalescing, I guess. Okay, let me open that. Open my terminal emulator. Malloc.py. Okay. Alright. We are using the default value of the flag here. And just change this. Free space malloc 1000. Okay, let's run without coalescing first. Oh, okay. Should I put that in less? Maybe. Hello, see. What distro are you using? I'm using Arch Linux currently. Okay. I mean PTR0 is gonna be the same. Oh, okay. Yeah, we are not using coalescing yet. Coalesce false. Okay. Okay. Yeah, over time I think the free list gonna be fragmented. Right. The size keep increasing. The size of free list keep increasing. Okay, size 11. Oh, there is even size 13. Okay. Size 14, size 15 here. Right, the fragmentation become worse, I guess. Okay. Alright, oh. Yeah, it's oh wait, what? Return -1? Interesting. So at some point we are run out of the, what is it called? Run out of the chunk, the contiguous chunk that can fit into the request memory. In this case, 9 bytes, because from this 31 chunk we don't have any chunk with the 9 bytes. So yeah, it return -1. I guess this one. Interesting. Okay. Non-coalescing. At some point, we won't have what is it? The contiguous, I guess, chunk of memory that is big enough for the request size, something like that. And then what happened when we use what is it called? Coalescing. Uppercase C here to coalesce. Okay. Wait a minute, be right back. Alright, let's continue. Okay. Okay. We immediately coalescing after the free PTR0 here. Unlock again, coalescing again. Oh, okay. So far we've coalescing. Okay. Size 1. Alright. So PTR4 is not free yet. We free PTR4 in this case, I guess. Okay. Oh, the fragmentation begin in this one. Okay. But then it become one chunk again when we free the PTR7. Alright. Okay. looks like oh, wait a minute. Oh, there is some. Okay, interesting. Alright, I think it has the same problem that at some point we won't have what is it called? A chunk of memory that is big enough, especially if we didn't free previous allocation. Okay. What is it called? Wait a minute. Okay. Maybe something like this. Have more occurrence. Okay. Have more occurrence of file allocation because of fragmentation. Something like that. Yeah, looks like quite a lot of fragmentation. Oh, okay. Okay, 300. Okay. 386 result. Wait, I think well, maybe it depends on how frequent we free the previous allocation, I guess. But yeah, I assume when we're coalescing, have less occurrence of file allocation because of fragmentation, something like this. What is the difference when using coalescing and non-coalescing for the free list? When non-coalescing, what is it called? The free list become more fragmented, I guess. The free list become more fragmented and causing more failure if we didn't have, if the fragmentation isn't big enough to hold the requested size. Coalescing, the free list become less fragmented and less failure. Depends on how frequent we free allocation, I guess. Because the fragmentation is less than when not using coalescing, something like this. Less fragmented and less failure, because the fragmentation is not as severe as the non-coalescing, something like that. And then how big the free list over time when using coalescing and non-coalescing for the free list. The non-coalescing free list is bigger over time compared to when using coalescing. When coalescing, how big it is, I'm still not sure. I mean, it depends on how frequent we free the, what is it called? The memory allocation, I guess. Does the ordering of the list matter when coalescing or non-coalescing? It depends on the what is it called? On the search free list policy, the one like best, worst fit, and then first, and so on. For example, when using worst fit, the ordering might not I'm not sure if the ordering matter or not for the worst fit. I mean, the worst fit is, what is it called? Looking for the space big enough to hold that. But yeah, when using best or worst fit, the ordering might not really matter because we are scanning all of the what is it called? All of the elements in the list. So whether we what is it called? Whether we put the biggest chunk in the front of the list or not. For best and worst fit, I don't think it won't matter that much. Ordering. Maybe it matter when we're doing coalescing. Like the list becomes smaller, right? Yeah, maybe something like this. What is it called? But yeah, that's not really about ordering. But using coalescing, or maybe this one, but coalescing the free list can speed up the search because the elements might be smaller than non-coalescing the free list, maybe something like that. So it depends on the search of the free list policy. I assume when using best or worst fit, the ordering might not really matter, because at the end of the day we are scanning all of the element in the list when we are using best or worst fit. But coalescing the free list can speed up the search because the element might be smaller than non-coalescing, right? Something to keep in mind. Okay. Alright. What happens when you change the percent allocated fraction dash p bigger than 50? What happens to allocation as it near 100? Oh, interesting. Not that 1% unlock. Oh, okay. The default is 50. Alright. More than 50. Let's try 60 then. Right, so should we use coalescing? Let's not use coalescing first, I guess. Oh, right. Okay, let's take a simple approach first. Okay. see any difference, I guess. Let me try 70 then. For element, 5 element, Oh, wait a minute. Percentage of allocation. Does that mean we have less free to memory? 1, 2, 3, 4. Compare that to this one. 1, 2, 3, 4, 5. Okay, interesting. Only 1 free. What? Oh no, 2 free. Okay. Interesting. Let me try 90. Okay. It is still 2 from 10 operation to, what is it called? 2 operation is free. Other than that, it is allocating memory. Let's try 95. What? There is no free to memory. Okay, interesting. Yeah. Okay. What happens when you change the percent allocated fraction to higher than 50? The free operation become less and less as we increase the allocated fraction. And then what happened to allocation as it near 100? At 95% allocated fraction, there is no free, what is it called? There is no free operation at all, I guess. So we are only allocating the memory without free any memory as the percent near 0. Near 0, Let's try 20. Okay, free and then free. Okay, alright. It looks like when the percentage near 0% allocated fraction near 0, every time we, what is it called? We allocate a memory, doing allocation memory, we are freeing those memory immediately. Like this one, we allocate PTR4 and then we are free those PTR4 in the next operation, something like that. As the percentage needs 0, we immediately free the previous allocation. Okay, What kind of specific request can you make to generate a highly fragmented free space? A highly fragmented free space uses a flag to create fragmented free list and see how different policies and options change the organization of the free list. Highly fragmented free space. Okay. I think if we want a highly fragmented free list, the easiest one is not using coalescing, right? It's gonna be more fragmented than when using coalescing. Okay. And then how different policies and options change the organization of the free list. We kind of already see that from the 4 questions here. Using worst, first, best, and also the sorting one, right? Use the test a flag to create fragmented free list. And see how different policies and options change the organization of the free list. Fragmented free list. Okay. We have 10 operation, right? Then maybe something like this. +1. Yeah, the easiest one that I can think is chopping that into small piece, I guess. 5 and then free that, and then 10 and then free that, 15 and then free that. How many is this? 1, 2, 3, 4, 5, 6. Okay. 20 and then free that, and then maybe 30 and then free that. Yeah, for the what is it called, for the 10 allocation, this might be one of the scenario to make the fragmentation worse, I guess, or big. I mean, we keep chopping up the big size here. Okay, if we are using different policy, For example, words. Words, okay. Kind of the same, I guess. Was and verse. Alright. Okay. Yeah, I will leave this for anyone who wants to explore this. And then let's move on into the paging introduction. Okay. Alright. It is sometimes said that the operating system takes one or two approaches when solving most any space management problem. They sometimes said that operating system takes one of two approaches when solving most space management problem. The first approach is to chop things up into variable size space, as we saw with segmentation in virtual memory, right? Chop things up into variable size space. Okay, unfortunately, this solution has inherent difficulties, in particular when dividing a space into different size chunks, right? When dividing a space into different size chunks, the space itself can become fragmented, and thus allocation becomes more challenging over time, right? We will still get fragmentation, but the question is that how to minimize those fragmentation, right? Thus, it may be worth considering the second approach, to chop up space into fixed size space. In virtual memory, we call this idea paging. Okay, and it goes back to an early and important system, the Atlas. Oh, okay. Instead of splitting up a process address space into some number of variable size logical segment, right? Variable size logical segment, for example, code heap stack, we divide it into fixed size units, each of which we call a page. Okay. Correspondingly, we view physical memory as an array of fixed size slots called page frame. Okay, we view physical memory as an array of fixed size slots called page frame. Each of these frames can contain a single virtual memory page. Each of these frames can contain a single virtual memory page. Okay. So the physical memory called page frame, and the virtual memory chunk or unit is called page. Okay. Page frame, or some people call this only frame, I guess, to reference the physical memory. our challenge, the crux, how to virtualize memory with page. How can we virtualize memory with page so as to avoid the problems of segmentation? What are the basic techniques? How do we make those techniques work well with minimal space and time overhead? Alright, that is the challenge. A simple example and overview. To help make this approach more clear, let's illustrate it with a simple example. Figure 18.1, page 2, present an example of a tiny address space. Tiny address space. Okay, only 64 bytes total in size. Okay, with 4 16-byte bits. 4 16-byte bits. Alright. Virtual page 0, 1, 2, and 3. Real address space are much bigger, of course. Commonly 32 bits and thus 4 GB of address space, or even 64 bits. Okay. In the book, we'll often use tiny examples to make them easier to digest. Alright, let me read the footnote. A 64-bit address space is hard to imagine. It is so amazingly large. An analogy might help. If you think of a 32-bit address space as the size of a tennis court, a 64-bit address space is about the size of Europe. Oh, okay. This one, page 0 of the address space, page 1, page 2, and then page 3. A simple 64-byte address space in figure 18.1. Physical memory, as shown in figure 18.2, also consists of a number of fixed size slots, in this case 8 page frame, making for a 128 bytes physical memory, also ridiculously small. Okay, 18.2, figure 18.2. So consists of a number of fixed size slot, in this case 8 page frame, making for a 128 byte physical memory. Okay, as you can see in the diagram, the page of the virtual address space have been placed at different locations throughout physical memory. The diagram also shows the operating system using some of physical memory for itself. Okay. The operating system using some of physical memory for itself. Okay, paging, as we will see, has a number of advantages over our previous approach. Probably the most important improvement will be flexibility. With a fully developed paging approach, the system will be able to support the abstraction of an address space effectively, regardless of how a process is the address space. We won't, for example, make assumptions about the direction the heap and stack grow and how they are used. Okay, so no assumption for the direction the heap and stack grow and how they are used. Okay. 18.2. Let me check here. This one, figure 18.2, a 64-byte address space in a 128-byte physical memory. Page 3 of address space, I guess. Page 0 of address space. And this one reserved for operating system. Okay. Page 2 of address space, page 1 of address space. I'm assuming AS in this case means address space. Okay, so the fix, what is it called? The fixed size here is 16 byte, I assume. So there is that. Another advantage is the simplicity of free space management that patching afford. For example, when the operating system wishes to place our tiny 64-byte address space into our 8-byte physical memory, the simplicity of free space management. Okay, when the operating system wishes to place our tiny 64-byte address space into our 8-byte physical memory, it's simply fine for free paths. Perhaps the operating system keep a free list of all free paths for this and just grab the first 4 free paths of this list. In the example, the operating system has placed virtual page 0 of the address space, KIS here, right, the address space, in physical frame 3, virtual page 1 of the address space in physical frame 7, page 2 in frame 5, and page 3 in frame 2. Yeah, sometimes people call page frame as frame, so something to keep in mind. Page frame 1, 4, and 6 are currently free. To record where each virtual page of the address space is placed in physical memory, the operating system usually keeps a per process data structure known as a page table. The major of the page table is to store address translation for each of the virtual pages of the address space, thus letting us know where in the physical memory each page resides. For our simple example, figure 18.2 page 2, the page table would thus have the following 4 entries: virtual page 0 to physical frame 3, virtual page 1 to physical frame 7, virtual page 2, virtual page 2 to physical frame 5, virtual page 3 to physical frame 2. Okay, it is important to remember that this page table is a per process data structure. Okay, per process. So does that mean we have a page table per process? Let's say we have 2 process. Does that mean we have 2 page table? Is that it? If we have 2 process, does that mean we have 2 page tables? This is the question. page table is a per process data structure. Most page table structure we discuss are per process structure. An exception we will touch on is the inverted page table. Oh, okay. If another process were to run in our example above, the operating system would have to manage a different page table for it, as its virtual page obviously mapped to different page table. Okay, so maybe the answer is yes. Page table per process data structure. So if there are multiple process, the operating system need to manage multiple page tables because its virtual page, its process virtual page map to different physical page. Physical page. Okay, maybe something like this. Alright, okay. Now we know enough to perform an address translation example. Let's imagine the process with that tiny address space, 64 byte, is performing a memory access. Okay, this one. Specifically, let's pay attention to the explicit load of the data from address virtual address into the register AAX, and thus ignore the instruction fetch that must have happened prior. Okay. Explicit load of the data from the address here into the register AAX. Okay. To translate this virtual address that the process generate, we have first split it into two components. The virtual page number, VPN, okay. Virtual page number. Okay, the virtual page number and the offset within the page. The virtual page number and the offset within the page. For the example, because the virtual address space of the process is 64 byte, we need 6 bit total for our virtual address. Okay, is 6 bit from this one, so it is something like modulo maybe. Let me try that. How to use modulo in Okay, thus our virtual address can be conceptualized as follow. Okay, virtual virtual trace 0 until virtual trace 5. And I assume we divide this by 2 bytes, right? So its virtual address here have 2 bytes of memory, maybe something like that. In this diagram, VA5 is the highest order bit of the virtual address and VA0 the lowest bit. Because we know the bit size 16 byte, we can further divide the virtual address as follow. Oh, 16 byte. Virtual bits number, okay, and then the offset. Why is the virtual bits number these 2? I mean, why not only 1? Is it because what is it called? If one, oh yeah, maybe because if we are using only 1, it's not gonna fit all this offset. Maybe, I mean, if we are only using 1, there's only 0 and 1, for example. So yeah, it's only 2, but with this one we might have something like this: 0 0 0 1, okay, 1 0 and then 1 1, maybe something like this. 1 2 3 4, 1 2 3 4. Okay, the bit size is 16 byte in 64 byte address space. Thus we need to be able to select 4 bits. And the top 2 bits of the address to just it. Thus we have a 2-bit virtual bits number. The remaining bits tell us which byte of the bits we are interested in. 4 bit in this case, we call this the offset. Wait, I'm kind of confused. Is one is this in bit, this virtual address, or not? To select 4 bits, we are talking about, oh, bit size is 16 byte. The top 2 bits to adjust it. The remaining bits tell us which byte of the bits we are interested in. 4 bit in this case. Oh, wait, let me try that. we need 6 bits total for our virtual address. Oh, so okay. I think virtual address is something like this, right? What is it called? 1, 2, 3, 4, 5, 6. Maybe something like this. Again, 6 bit for our virtual address, right? So one virtual address here contains 6 bit like this, I assume. But why VPN or the virtual page number here in the virtual address 5 and virtual address 4? Is this what is it called? The representation of one virtual address, the bit in the virtual address. Maybe. Count this offset. When a process generates a virtual address, the operating system and hardware must combine to translate it into meaningful physical address. For example, let us assume the load above us to virtual address 21. Turning 21 into binary form, we got this one, right? 1, 2, 3, 4, 5, 6. Okay. And thus we can examine this virtual address and see how it breaks down into a virtual page number and offset. Okay. So looks like this is the, what is it called? The representation of one virtual address, right? One virtual address. At first I thought that this is the representation of address space, the virtual address space. But it looks like this is the representation of one virtual address. Maybe something like that. And this one is virtual page number, right? And then this is the offset. Thus the virtual address 21 is on the 5th. Oh, okay, this one. So all of the bits is the offset. Okay. The 5th byte of virtual page 1. Okay. And then the virtual page number is also this one. The whole set of binary 0 and 1. Thus 1. Okay. With our virtual page number, we can now index our page table and find which physical frame virtual page 1 reset within. Okay. In page table above the physical frame number PFN, also sometimes called physical page number or PPN, is 7. To binary this one. Thus we can translate this virtual address by replacing the VPN with the PFN Okay, replacing virtual page number with the page frame number and then issue the load to physical memory. Okay, there's translation, right? Virtual page number translate to this from the page table. I mean, again, yeah, we page table 7. In the page table above, I assume it's this one, I guess. Okay, we take a look at the page 1, right? Because again, the virtual page number, or maybe the index of the virtual page is 1, right? So virtual page 1 here. Virtual page 1 is in the page frame 7. The page frame 7 at the binary 111. Thus we can translate this virtual address by replacing the virtual page number with the page frame number and then issue the load to physical memory. Figure 18.3. Oh, we use the offset bits directly. Okay. Alright. Page frame 0 of physical memory. Okay. Note the offset stay the same, right? That is, it is not translate because the offset just tell us which byte within the page we want. Our final physical address is this one, 117 in decimal, and is exactly where we want our load to fetch data from. Figure 18.2 page 2. This one. Yeah. Page 1 is from, I think, 113 until 100 and or maybe 112 until 127, because we start from 1, right? 100 from 112 until 127. And this one, 117, is within this range. Okay, and is exactly where we want our load to fetch data from. With this basic overview in mind, we can now ask and hopefully answer a few basic questions you may have about paging. For example, where are these page tables stored, right? What are the typical contents of the page table, and how big are the table? Does paging making the system too slow? This and other big questions are answered, at least in part, in the text below. Read on. Okay. Yeah, where are these page tables stored? That is an interesting question. Okay, I think we will continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.